Okay, thanks everybody for joining us today with the CISL seminar series. We're pleased to have Dr. Tasha Snow with us from the Colorado School of Mines. Tasha is a research associate at the Colorado School of Mines working to better understand high latitude ocean and glacier change and how it will impact the planet. Her work focuses on how oceans interact with glaciers in Greenland and Antarctica, and she's developing new ways to apply satellite thermal infrared imagery to study heat transport within these systems. And also of interest to the CISL audience is she's doing a lot of this work on the commercial cloud at this point through some NASA grants and other avenues. And CISL's looking into some similar capabilities, so we're excited to hear how that work's going for you. All right, thanks, Tasha.
Got it. I'll start over there. Thank you for having me. Mic issues. I know a lot of people are online, so it's an important thing. I will be talking to you a bit about new applications for thermal infrared imagery in Antarctic glacier-ocean research using cloud computing workflows, and I'm thinking about open science and different ways that we can apply some of the remote sensing and field observations that we have. I'll start with a background in ice-ocean interactions in Antarctica, and then get into some of the new techniques that we're using and more comprehensive and collaborative ways of applying them. Before I get started, I want to acknowledge all of my collaborators who have worked on the projects that I'll be talking to you about today. They're across the US and international, and they've done a ton of work on what you'll be seeing today, not just my work. So Antarctica, of course, all of us know Antarctica is important for the climate of the globe and is a really big wild card for sea level. So we really don't know how much sea level is going to be coming from Antarctica in the near future. Around Antarctica, all of the melt and ice loss occurs at the glaciers and ice shelves that are shown here in the purples and blues by the relatively fast-moving ice that comprises them. Of that melt that comes from these areas, half of it is derived from melting by the ocean. So heat transport by the ocean is extremely important for the ice loss and sea level rise that we'll be expecting from Antarctica. The glacier ocean systems that we have in Antarctica look a little bit like this. We have the glacier on the left with the ice shelf as the floating portion of it. The water column around Antarctica, or much of Antarctica, has winter water in the surface that's relatively fresh and cold. And the water below it is circumpolar deep water that is warm and salty. And so this resides usually below 300 meters, sometimes a little bit deeper. And this is the water that we worry about in terms of bringing heat towards the glaciers and ice shelves. We have analogs to these in Greenland that are polar water in the surface and Atlantic water at depth. There's kind of similar systems in that respect. The way that we transport this heat towards the glacier is the water comes in at depth, it gets to the grounding line, it melts the glacier there. That melt is fresh and buoyant, so it rises towards the surface as a plume. And once it's at the surface, it flows away, whether outwards or parallel to the front of the ice. And so that's kind of the glacier or the melting scheme that we have. And this ice-ocean interaction, these processes are relatively new to our understanding. So we began to start to realize that West Antarctica especially, not just Antarctica, is really important to the climate system and would be potentially responding rapidly to carbon dioxide increases in global warming in the near future. But at that period of time, we had very little understanding of Antarctica. We had no full map of Antarctica, very few measurements, and it wasn't until the RadarSat Antarctic mapping mission in 1997 where we actually got our first full look, our first map of Antarctica. And So before 1997, RadarSat is a satellite that we used to map Antarctica at that time. Because it's a radar satellite, it is side-looking, and so it actually never looked into the center of Antarctica during its orbit. And so you get this giant pole hole, which, I mean, conspiracy theorists enjoy talking about. But what happened was, in a collaboration between NASA and Canada, because Canada owns RadarSat, Canada decided to turn it to be left-looking. And so we actually filled in the center of Antarctica, and we get a pretty dense measurement of Antarctica there, where we really thought nothing was going on. We finally had that full map. And so from there, we start to understand a lot more about the changes that are occurring in Antarctica. So in 2002, we start to realize how important basal melting by the ocean, is for Antarctica. Then we start to notice that there are ice shelves that are collapsing in Antarctica, and that's causing a lot of thinning and acceleration of some of the glaciers in Antarctica in the early 2000s. And then more recently, we're starting to think more about tipping points. So are there places that are beyond return for these glaciers? Are they becoming unstable? And we really don't know the answers to that yet. We really don't know how stable some of these are, and so this is ongoing research. This is all really new, and we're just starting to get the data to be able to do that. So over the last decade, a lot of big programs in both Greenland and Antarctica have started to gather tons and tons of measurements. This program, the International Thwaites Glacier Collaboration, I'll talk about a little bit later too, is studying the ice, the ocean, and the atmosphere, taking a ton of measurements in West Antarctica, where most of the melt in Antarctica is taking place, in the Amundsen Sea. So if you've heard of Pine Island Glacier or Thwaites Glacier, that's where this work is focused. And it's collecting a lot of data, so we're getting bigger data sets. However, most of Antarctica is still pretty unknown. So this is a map of where we have data and measurements around Antarctica. And what you'll notice is that in the light blue colors around the continent, most of those places are not covered in red. So we still have a lot of places around Antarctica we have very little knowledge. And to fill in some of those gaps, we can use remote sensing. So this is NASA's constellation of satellites. Many of those satellites are useful for studying Antarctica. There are a lot of other space agencies. And so we're trying to think of new ways that we can use remote sensing to fill in some of those gaps in data collection. And so the work that I'm doing is to try to understand, are there ways that we can use remote sensing to study heat transport towards the ice? And some of that work I did during my PhD, where I used moderate resolution imaging spectroradiometer data, sea surface temperature data, to show that we could use remote sensing data as a proxy for surface and subsurface water temperatures in places where the oceanography worked to do that. So some places you can do this, some places you can't, and there's a method for doing that. But that we could do that in southeastern Greenland. And so this is important because most places, as I said, don't have field observations of temperature variability from the ocean. So we're starting to fill in those gaps and show that we could use thermal infrared to do that. And another cool thing that you can do with this remote sensing thermal data that will build upon what field observations can do is that you get a much more spatial and temporal, like much better coverage, spatially and temporally, of an entire system. So in Greenland and Antarctica, as I mentioned, you have these two water masses that are very different temperatures. That means that we can potentially use sea surface temperatures to kind of study them and watch them and have high temporal coverage of the changes that happen, at least at the surface. So this is a video over the course of a few hours that shows an intrusion of warm water across the continental shelf, moving more than 40 kilometers, all the way towards Helheim Glacier, which is in the top middle up there. And this is a phenomena that you can measure by a mooring that's sitting in one place, kind of, but you have no idea of the spatial context. And most of the ship observations that you might be able to use are just of, you might catch this, you won't get the full picture. So the remote sensing side of this adds beautiful context to the processes that are happening. And so with this, we could actually show that these intrusions occur at the same time along multiple troughs around Greenland, shuttling warm water towards the ice. And this is something that we hadn't noticed before. So with this new huge data that's coming out of remote sensing and the new field observations, what are the new tools and applications we have for better utilizing them? So I'll talk about 3 different projects that we have. The first one, I'll talk about how we can fuse remote sensing and field observation data to study the Antarctic coastal current as a use case, and to look at variability in that coastal current in ways, we have very little understanding of the coastal current in Antarctica, but understanding the variability is something we just really don't know about most currents in Antarctica. From there, I'll move on to talk about how we can add to that kind of understanding using machine learning, how new state-of-the-art statistical methods can help us answer questions that we've never been able to answer before. And from there, talk about where we're going next. So as we have this big data in ice ocean analyses and any field that you may be in, how the cloud and open science principles are helping to move the needle and push that forward. So starting out, thinking about the Antarctic coastal current, this is work done with the International Thwaites Glacier Collaboration to look at the seasonal and interannual variability in the coastal current. And just for a little background on why this is important to begin with. So the Antarctic coastal current, we know is near the coastline of Antarctica. We have, there are studies that have been done in the peninsula and in the Bellingshausen Sea that have found the coastal current and show that it's there. It's fast, it's shallow, it flows to the west, and it's really important because it carries a lot of meltwater away from the ice shelves. So as the coastal current moves around Antarctica, and it flows around much of Antarctica, but we don't know about how much of Antarctica, as it flows at least on the western side, it goes over to the Ross Sea into that big divot at the bottom of Antarctica there. And that's an area where we have deep water formation. So the amount of meltwater that goes into that area is really important for driving deep water circulation around the globe. And so as this current moves past a lot of West Antarctica and gathers this meltwater and increases, which the meltwater concentration increases as you move towards the east, that becomes really important. Understanding that becomes really important for global ocean circulation. On top of that, the variability in the coastal current affects heat transport towards ice shelves. Whether it's at the front of an ice shelf or if it moves away, that changes the heat that can be transported. So it's a really important thing to know, and we know very little about it. As I mentioned, we're using lots of different data sources for this. So the field observations we have, we're using water velocity from an acoustic Doppler current profiler from the ship. We have shipboard CTD, which gives us conductivity, temperature, and depth, and from that we can calculate salinity. The ocean glider and seal tag CTD measure the same. And then the remote sensing component that we're using is sea surface temperatures from MODIS and from Landsat. So MODIS provides the core spatial resolution, but high temporal frequency, and Landsat provides the high detail and lower temporal frequency. Now, the reason why we think we can use remote sensing, this thermal data in Antarctica, is because we can use meltwater as a tracer. So meltwater is relatively cool in comparison to the ambient water, especially in summertime. And so this is a map made from MODIS sea surface temperatures here on the left-hand side of the picture. And what you'll notice is along the coastline, there's these blue areas, this cold water. And on the right-hand side, we have a model from MIT GCM that's modeling the surface current. And the surface current is cold in a lot of, the Antarctic coastal current is cold in specific locations on the southern side of the Amundsen Sea here and in the northeastern side. And so this makes sense because meltwater is cooler, and in these locations, you have a source of meltwater from the ice shelves. You'll notice that kind of on the bottom right-hand side of the image, there's not a lot of this cool signal, and this is because we don't have a meltwater source just upstream. So this is likely a place where we can't use thermal to study the coastal current, whereas in the other locations, just downstream of the glaciers, the outflow from those glaciers will allow us to study the coastal current because that water gets entrained and follows the coastal current. So looking at a little bit of the field observations that we have, the coastal current in this is water velocity in the eastern side of the Amundsen Sea, and 2 different transects taken a week apart. So the coastal current is in the very top 100 meters over here on the right-hand side here, so that's southward flow, and then down here in the bottom, there's potentially a couple different branches of the coastal current. And these different branches can actually create a lot of confusion, and so this is probably partially why we can't really track thermal data south, or the coastal current south of this location, because the temperature signal gets really mixed in. Along the southern side by Thwaites Glacier, the coastal current is also at the surface there. So we can verify, we can see this from shipboard measurements. But the shipboard measurements, as you can see, are from 1 year, a few different days. We can start to better track the ocean properties using seal tag data. So these seals are tagged at the beginning of the year. When the ship is there, they wear these tags. I should have put a picture in here. They have these tags, they look like unicorns. It's pretty ridiculous, that they wear for about 9 months and measure all of their dives. And they go wherever they like around this area, and they're capturing up to 4 dives per day for each seal. So we have maybe 10 to 12 to 15 seals each year that are tagged, and then their tag falls off when they start to molt 9 months later. But what's really cool is we get a ton of data when the ship isn't there, so during winter time. And this is an example of an aggregation of some of the transects that I've taken. You don't get to choose where you get to take these transects, but I have it showing an average from summer and winter time from across 2014, 2019, and 2020. And this is temperature on top, salinity in the middle, and water velocity on the bottom. And what you'll notice here in the velocity at the bottom here is that I've highlighted the Antarctic coastal current. What we can say between summer and winter time is that the coastal current is faster, it's stronger, and it's further offshore in summertime. And that makes sense because we have a lot more meltwater in the system. So we can start to answer different kinds of questions with this big data that we've retrieved only in the last few years. And then we can start to pair it with the remote sensing data. So MODIS has a robust sea surface temperature product that it provides, though it's not ground truthed in Antarctica, I will say. But Landsat doesn't have its own product, so I have to produce my own. And actually for this work, I only need to do the temperature, look at the temperature gradient. So I just produce a land mask, a scene-specific ice and cloud mask, and then extract the surface pixels from the thermal band 10 in Landsat. And this is kind of what it looks like this is in the southern portion of the Amundsen Sea. This is Thwaites Glacier right here, the Doomsday Glacier that they talk about in the news sometimes. Please don't repeat that I said that. We're trying to get away from the Doomsday Glacier. But looking at this image, this is from Landsat looking down. Thwaites Glacier is at the bottom of the image. We have ocean as the color, as uncalibrated sea surface temperatures. There's cloud here and ice. And the coastal current is here in the cold pixels that you can see, the yellow pixels, running right up against the front of Thwaites towards the west. And what we can do, just as a simple measurement to start, is measure the width of this current based on the temperature gradient. And measuring that over time, this is showing that from 2016 to 2018, it's from December down to February on the y-axis, and it's the coastal current width along the x-axis. And what you may notice is that the coastal current runs about 15 kilometers wide in this area on average, but there's a bit of deviation, and that variability can be related to changes in meltwater influx, to diversions of the coastal current away from the ice front where we wouldn't be measuring it, and widening and narrowing from storms, as well as error from the method, right? If there's no cold water, meltwater, creating a temperature gradient, we can't actually measure this. But this is really cool because we can calculate how wide we expect this current to be in this basin, and then we can measure it using sea surface temperature and start to get at questions about the long timescale changes in this current that have never been recorded. So this is kind of the work that we're doing and how we're starting to merge these kinds of data sets together, combining thermal measurements with the field-based observations to get at something in a way that we've never been able to do in the past. We really don't know the current variability around Antarctica. And that variability, as I mentioned before, can impact the heat transport towards the glaciers, so we're really working to figure out how that interaction might impact some of these glaciers that are retreating rapidly in that area. So with that, I want to talk a little bit more about how we're starting to automate these remote sensing processes to work with the field data with the aid of machine learning. And this work is investigating the impact of some ice-ocean interactions and how they co-evolve with ice shelf stability, again, in the same area we just looked at. So I have some words on here: Antarctic basal channel and persistent polynya that I'll describe here. So here's, again, another schematic of the water column in Antarctica. And so here the warm water is coming in, it's melting, it's creating a plume, right? The plume is turbulent, so it entrains warm water into it as it rises towards the surface. And when it's rising, what's really interesting is it finds the topographic highs in the bottom of the ice shelf and starts to follow the same path over time. The same plumes rise, they find the same topographic highs. And because that plume's warm, it starts to incise this over time. And what we create is a basal channel that is very similar to like an upside down river. And it straightens out over time, and so these plumes follow this path over and over. As these plumes follow the basal channel and get to the edge of the ice front, they can either exit out at the same depth if they're not very buoyant, or if they're buoyant enough, they'll rise to the surface and carrying that heat with it. So if you have sea ice that's formed on the ocean right in front of the ice shelf there, if you have that there, then that warm water, that plume, will melt a hole in the sea ice, and that's called a polynya, an open water area surrounded by sea ice. And it's persistent because it occurs at the end of these basal channels where the outflow occurs, and it occurs in the same place seasonally multiple years in a row. And what's really amazing about these polynyas is you can see them from remote sensing because they're at the surface. So potentially the variability in these polynyas can tell us a bit about what's happening beneath the ice shelf in terms of basal melting, in terms of ocean interactions with the ice, in places where we have no measurements. We have no measurements beneath the ice. We have no idea how basal melting is changing on short time scales, and so we're hoping to be able to figure out the mechanisms that drive the polynya variability so we can start to extrapolate back in time. And we're doing this, we're trying to do this at a lot of different polynyas, or all of the polynyas around Antarctica. They're shown here with the red dots. But we're starting off with a case study in the Amundsen Sea, which I've blocked off here. And we'll kind of zoom in to see what these actually look like from satellite. So this is an image from MODIS looking down at the Amundsen Sea. We have Pine Island Ice Shelf here, and we have Thwaites Glacier. So this is all land ice around the bottom edge here. This is open water. This is Pine Island Bay. This is sea ice. So this is that ice that forms on the ocean. And then you'll notice this dark spot here. This is the persistent polynya and the basal channel. I'll zoom in with Landsat. You can see how much more detailed it is. This is the persistent polynya and the surface expression of the basal channel. So we can actually see this from satellite, and we want to investigate the mechanism driving the variability in that polynya. So to do that, we want to automate detecting this polynya using a cloud-based workflow that makes it more collaborative, more transparent, and reproducible. We're using various packages, open source data packages for data ingest and structures, data processing, visualization. And then we're using Landsat, MODIS, and Sentinel-3 data to do this. And what we get out of this is what's on the right, just a shape file of this polynya. but we're able to do it at very fine scale. This polynya is only at most about 1 kilometer across. So very tiny features that we're able to look at now, and we're able to do this eventually around all of Antarctica for every image that we have. So this is starting to get into something that you really need to automate. And so as part of this, we can do classifications, but with new emerging technologies, we can start to input information about the physics, about this, to be able to detect the polynya as well. So we know that these polynyas are associated with basal channels and the front of an ice shelf. So being able to incorporate that information into a machine learning algorithm will help to automate this. And so to do this, I have a couple undergrads who have helped me with some of this work. Ojin Lee is an undergrad at Columbia University. She created these amazing detailed labeled data sets for a machine learning algorithm that will help to train it. And then Michael Field is an undergrad at the School of Mines. He just graduated and is moving on to a grad program at University of Florida, working on geostatistics in ice research. And he created a unit to be able to detect the front of the ice shelf in an automated way using some of the training data from Ojin. And then now that he's moved on, Ojin is working to refine this model. And these start to provide information for the eventual physics featurized segmenter that we're creating. This is being developed by Ellie Abrams, who's a grad student in statistics and data science in Berkeley. And so she's building this cutting edge algorithm to pre-process and do some of the predictions on finding polynyas, but using physics featurization. So incorporating information about the basal channel, about the ice front, about the time of year, putting that information into places in the algorithm that make sure that the algorithm knows that these physics are important. So a lot of algorithms, if you've seen, make their decisions based on some of the ambient information in the scene. Like if you've seen like the horse identification that they have online, where they figure out that the reason why this algorithm can identify the horse is because of, the rider or whatever fences or whatever in the background. We don't want our algorithm making decisions on things that aren't relevant, because this will make it more translatable to other places in Antarctica. So we're incorporating that. And from that, we get a time series like this from 2013 to 2021. This is showing the aerial extent of this polynya. And what we can see from this is the seasonal and interannual variability. It's much larger in some years. It's open a different amount of time. Some years, sometimes only for a month, sometimes for only 6 months. And we can start to answer questions about how this variability relates to mechanisms beneath the ice shelves from that. On top of that, we're using thermal data in conjunction with surface elevation data to think about how sea ice may be thinner in these polynyas because warming is occurring there in wintertime, or to look at surface plumes to see if we can see plumes associated with warm temperatures. And this work was done in the ISAT-2 Hack Week. I'm not sure if any of you are familiar with Hack Weeks. ISAT-2 is a laser altimeter that measures surface elevation of the planet. And they have a Hack Week where people from a range of levels of computing background come together to learn how to use ISAT-2 data. So there's a lot of coding and training. And by the end, there's a project that everyone participates in. And so I led a project on this work with 5 graduate students that are listed there. Some of them had never used ISAT-2 data. Some of them were pretty beginner in Python. But because we worked in a cloud environment and we were trained how to use it, they were brought up to speed so fast that we could do this sort of project in 3 days. And so this is going to be something that we publish here in the near future, but it really allows collaboration and science to be accelerated. On top of that, we're doing a bit of data fusion. And so I mentioned before the seal tag CTD data. Elena Savage is a grad student at the School of Mines who just got this paper accepted literally a few days ago, where she used the field observations and fused it with the thermal data to show that where we see warm surface temperatures in the seal tag data, we also see warm thermal anomalies in both Landsat and MODIS. And that This could be measured in wintertime. So normally Landsat is not usually taking imagery in wintertime, so we don't have a ton of images from wintertime because no one thought it was important to take images. But what we're showing is that there's a lot of information we're missing because we could have the thermal imager on. And so this is some of the work that we're showing. We can monitor these year-round using thermal data. So all of these projects are kind of work together, as I'm showing here, with the neural nets and the segmenter and the sea surface temperatures all working to kind of understand plane variability. But what's really cool about this project is we're all working in similar environments. So we're using a cloud computing environment. That's what I'm representing in that box over there. It's a Jupyter Hub that allows us to have the same environment to code and be able to move our code around really easily. Next person uses it. They have the same environment, all working in the cloud. So this gets to my last piece, which is talking about where we're going next. So as I've been thinking about big data and using the cloud has become a big push for NASA for furthering our open science principles and the goals that we have. And from that, I've helped to found CryoCloud, which is a cloud computing platform for NASA cryosphere communities, and it's open cloud infrastructure. And so just to give a little bit of background on this open science push, this is coming from my perspective working with NASA. So NASA decided a little ways back that science done in a fundamentally more open way is the future. And so open science is a collaborative culture enabled by technology that empowers the open sharing of data, information, and knowledge within both the scientific community and the public to accelerate scientific research and understanding. And NASA's created this huge push to make their science more open, culminating kind of in the open source science initiative, where their goal is to make science more transparent, inclusive, reproducible, and accessible. And under that umbrella, they formed the Transform to Open Science program, which is helping to lower barriers to entry and to really push forward innovation to reach these science ideals. And so they built the Open Science Core, the Open Core, which is shown here at the bottom if you want to check it out, where they're teaching scientists how to do open science in their current science workflows. So this is kind of pushing open source science to the forefront, and within that, this is like a 5 to 10 year initiative. NASA and now the rest of the federal government, federal agencies, and about 80 academic institutions have all declared 2023 as the year of open science to really accelerate that push towards open science. And under that umbrella, as I mentioned, the cloud is one place where they're trying to push open science because you can democratize science with the cloud. And it allows you to work with large amounts of data without downloading it. So just as a little background in the cloud, if you're not familiar, the cloud is in the internet. Basically, you leave your storage there, your data storage, your servers, all your compute can be done there. Anything that uses internet or a router is outside of that. And so when you have it all in one place, the computing can be done very rapidly. And we need that because as we get these big data sources now, these big data sets, we can no longer download that onto our own computers. We need to leave it in the internet. And so we can build these really specific tools that we need for the work that we do. We can put them into the cloud, do everything much faster, and not have to bring that data onto our computers. And so what this creates is making the cloud kind of this digital watering hole. So we all have this shared resource of water that we need. It's too big to bring onto our computers. Lots of people need it. And so when we have the cloud, we can start to use disparate kinds of data. Diverse communities can all work on it to ultimately connect society and impact decision making at a time scale that's much more rapid than we've ever been able to do in the past. And so this kind of cloud idea is really important, and out of that came CryoCloud and sort of NASA's push. I put in proposals last year to build CryoCloud after I went to an ISAT2 science team meeting. So the science team runs the mission for ISAT-2, and they have a meeting twice a year that I went to last May. And in that meeting, they had a cloud computing panel, an open science panel, where the community, the team, expressed a lot of worry about cloud computing. So they expressed that the cloud has non-intuitive pricing structures, computing options, and infrastructure. The documentation is poor, it's costly to use. People were racking up thousands of dollars without realizing it in a few weeks. There's a time to transition your workflows. People worry about intellectual theft in the collaboration of open science, and that the cloud is not obviously more collaborative or faster. And so myself and Joanna Milstein, who is a graduate student at MIT, were sitting together and really felt that this was not the experience that we had in working in the cloud. And the reason why is because we worked with the International Interactive Computing Collaboration, 2I2C, which is a nonprofit organization that builds cloud computing platforms. And we worked on this. And working in this cloud computing environment, we found that we didn't have any of these issues. So we decided to partner up with 2I2C to build CryoCloud as a cloud computing platform with bumpers. The goal of CryoCloud is to be a simple and cost-effective managed cloud environment for training new users and transitioning them to cloud workflows. And in doing so, we also wanted to determine the best practices for working in the cloud, because most of the transition that we need to make here is a cultural change, and the technological innovations actually won't contribute to the success of these new technologies as much as those social improvements. So we're really working to understand how the community works in the cloud as well. The CryoCloud is built and developed for cryosphere scientists specifically, and it's built by cloud engineers. So it's built with the best expertise possible, rather than scientists having to build this themselves. And it's built to help people process their data faster and democratize science. CryoCloud is meant to be persistent for at least 3 years. So a lot of cloud computing environments, like with Hack Weeks, get stood up for a week or a month or whatever, and then people have to get off. We're providing a consistent daily usage computing platform for our researchers. We provide small instances for all of our users with the option of bringing their own AWS credits, so they can use larger servers if they bring those credits. We're developing new tools, so personal cost monitoring tools to understand your usage, and improving intra and inter-hub collaboration tools. And these tools will be eventually built into the Jupyter infrastructure, because some of the people working on CryoCloud are developers for Jupyter as well. And then on top of that, 2I2C is a very young nonprofit, and so we're helping 2I2C to scale up by taking community surveys, getting feedback and guidance, and all of that also helps us to better understand best practices for our community. So if you want to check out what we built, it's at cryointhecloud.com. That's where we house all of our tutorials and training and resources. And then the CryoCloud Jupyter Hub is located there as well. The GitHub is where we keep all of our code. We have a Slack channel, community office hours, and we're also doing a lot of community building. So we're talking with a lot of the cryosphere communities out there, figuring out what tools they need, figuring out how we can start to develop new tools in CryoCloud that can help us to access data more easily or to make their lives more easier, so communication and collaboration. Tools that we're starting to think about are how do we access things like Arctic Data Center, non-cloud data more easily from CryoCloud? How do we interface with an HPC from CryoCloud and bring that data back and forth really easily? These kinds of questions help us to interface with other communities and help us to stop it helps to reduce redundancy in the work that we're doing, to make sure that people who are doing different kinds of projects are working with each other, and we're really enhancing what each group is doing rather than competing or doing having a lot of redundancy in what we do. What this kind of looks like if you actually work in our Jupyter Hub is here on the left. This is a tutorial notebook that we have that helps run, or that runs ISAT2, MODIS, and Landsat data together. And it uses the tools up there on the right, IcePix, X-Array, and Earth Access, which are open source tools. IcePix is a library for accessing ISAT2 data specifically, and Earth Access is for NASA data. And what's really cool about all of this is that not only do we have our users working, using these tools that are really under huge construction and development, but we have the people who are the developers for these tools also in the same environments. So what that means is as development is being done on these tools, our users are putting them to work immediately and finding all the bugs, and it really accelerates the feedback and collaboration that happens. And so kind of in the same kind of vein where we think about, collaboration and communication and being able to accelerate that with the cloud, this sort of idea works for any field, right? You can fill in ice-ocean interactions or cryosphere with whatever your field is. But it really starts to get at the open science culture that we'd be able to realize as we move into the future using the cloud. And so what I kind of want to leave you with are some of these open science principles that we're hoping to push and that help make this more successful. So those open science values are intellectual generosity, humility, right to participate in science, and that everyone deserves to be treated with dignity and respect. So kind of digging into what each of these is, what I mean by intellectual generosity is that we are openly sharing our ideas, that we're advancing others' understanding and having constant communication, which helps both to reduce the scarcity model. It helps us to reduce redundancies because we know what's out there. We stop reinventing the wheel because we're sharing the basic things that we all need, like how to access a data set or how to build an environment. People don't need to do that anymore. As a scientist, you want to spend your time on science. So we end up reducing competition, enhancing collaboration. We're not all working on the same project at the same time, racing to try and get the first paper out on it. We can start to answer different parts of the question at the same time and really build as a ladder rather than all in one direct or in a much slower progression. On top of that, intellectual humility kind of gets at the fact that while we're scientists and we're creating all this amazing new knowledge, what we build is really a small portion of the entire body of knowledge. And what we build, it really stands on the shoulder of giants. So keeping that in mind and having intellectual humility, we can start to give and receive criticism with grace. So when we have gaps, we can start to communicate that more easily, give people feedback. It goes along with inclusivity and diversity and that sort of thing. Being able to give that sort of feedback and receive feedback in a positive and constructive way really will start to help us find solutions much more quickly and in a much more robust way. On top of that, right to participate in science is kind of democratizing science. This means that no matter where you are in the world, no matter what kind of computer you have, it can be a $36 Raspberry Pi, you can be able to access the data and science and the compute infrastructure that you need to do science. And this means that we can start to bring data into local places that have been previously underserved. I was talking to Doug earlier and he was talking about how you guys have HPC resources and that some people can access that more easily. And what the cloud allows us to do if people have access to the cloud is that they no longer need to have that technical expertise. They no longer have to have a giant computer to do huge compute. You just get onto the cloud, you access the server that you need, it's super flexible, and you can do the science that you need. And that makes a lot more impact in these local places where we haven't historically had science and data present. And now last, everyone deserves to be treated with dignity and respect. This goes along with diversity, equity, and inclusion. Science is meant to be objective and constructive, and having more voices in the mix will help us to find more robust solutions and to build a more inclusive environment. And it improves the quality of solution that we have for the global problems that we have. And so all of these together, what I hope you take away from this is thinking about open science not as the technological innovations that we have, not as a product, but as a process. So this is really going to be a culture shift for all of us. And it's a really good one because it's going to increase the amount of impact that we have in the world. It's going to improve our ability to collaborate and communicate with each other, and really move the needle forward for the global problems that we have to bring answers to those much more rapidly than we have before, right? The disconnect between science and policy making will hopefully be closed when we can start to do this together and much more rapidly. So with that, I want to close giving a little summary here. I've showed you how we can combine thermal imagery from satellites with field-based observations to better understand ocean circulation around Antarctica in ways we haven't been able to do before. When we integrate machine learning, and we do this through interdisciplinary collaborations with people like data scientists, we can start to answer questions in unprecedented ways, looking at tiny different places across all of Antarctica for every day that we have imagery is a really cool new thing that we can do with this big data. And at the end of that, ice-ocean research and any sort of scientific research in the cloud using the open source science principles that I talked about will accelerate science to meet the global need that's out there. So with that, I'd like to thank you for joining me and recognize my funders here. And definitely check out if you want any of these resources or want to reach out, you can do that there. With that, does anyone have any questions? Yeah.
Okay, I'll hand the microphone.
Can we take questions from online? How does this work?
Yeah, so
I mean, we'll start here for sure, but.
there was a Slido,
Oh, you have it down there.
There's a Slido link, I think, as part of the meeting invite. Is that right?
Okay.
So if you have questions, please add them onto Slido, and Kristen will read them for us.
Hi, Tasha. It's a really interesting talk.
Thanks.
Really great. So I have a little naive question about cloud computing. So I mean, I'm a HPC user, right? So I was wondering, like, what's the difference between, say, open computing and, say, granting everyone access to an HPC? Is it mainly like the infrastructure that's in place for easy data transfer, or I mean, am I missing, like, what's the main difference?
What's the main difference between HPC and cloud computing, and how people can access it? So for HPC, these are, I mean, the resources are pretty limited for HPC in terms of like who can access it and the sort of credentials that you need. For us, cloud computing, all you need is a GitHub authentication, a GitHub user ID, and we add you to our team. And so yes, if you're not a part of our team, you don't get access, but once you have access to it, you have full access to the different servers that we have. On top of that, what I didn't mention is that cloud computing can be really cheap, especially when you have someone like 2i2c building it for you. So right now at Berkeley, they're running classes that have 2,000 students in them for $1 or $2 per student per semester. So you can do massive amounts of work. Lots of people can use this for very cheap. Obviously, if you're doing big compute like you would on an HPC server, that gets to be a lot more expensive. So that's kind of where the two can work together really well, is if you need to do a lot of compute, you could access the HPC to do that expensive compute that you might do for a small fraction of the time that you have. That you're working and computing. Most of our work is done using very little compute, right? So you're building a lot of the code, all of that happens, and you can do that for very cheap in the cloud. So they actually complement each other. But you don't need, the cloud computing infrastructure looks exactly the same as you have on your computer. So I use Jupyter Lab on my computer. I use Jupyter Hub in the cloud. There's our studio that you can use. It's super modular. You can use MATLAB now. We actually have a MATLAB image in our cloud. So it looks exactly the same as your local computer. Hopefully it can access HPC eventually. That's one of the things that we want to make sure we can do. But yeah, that's kind of, hopefully they're complementary of each other, but hopefully the cloud can provide, like I can bring 100 people into the cloud tomorrow for a team or an event or a team event, or like if a response needs to be made to some sort of like climate disaster that happens, we can do that very rapidly. I can provide it for our Greenland researchers, and it costs me virtually nothing to do that.
Thanks.
Yeah. Sorry, long-winded.
We do have a couple questions from the virtual audience, so I'll read one right now.
Yeah.
One from Ben. It seems that having the source satellite data cloud resident is critical for controlling some of the data ingest/egress cost alluded to by others. In your experience, are all the key data sets equally available? And if not, where do we need to focus to help the research community?
So the data sets are not equally accessible. NASA might be, a decent place for data, kind of, but we're finding that it's actually like been done very haphazardly. Metadata and data formats are increasingly important as we move into the cloud. Legacy data formats are being migrated into the cloud, and they are inaccessible by most of the infrastructure like Xarray or Pandas in Python or other, I'm not sure what they are in R or whatnot, but these programs can access data from URLs, but they cannot open legacy data formats. And so binaries and old HDF files, and when you put zip files into the cloud, these still have to be downloaded. So in that respect, we have a huge problem in terms of metadata and data formats, because every scientist has been out for themselves in terms of deciding how to put it into archiving. And then on top of that, there's some data that everybody uses. So Landsat, for instance, is now in the cloud. It's super accessible, and it's probably within one of the most widely used data sets, so it's great that it's in there. There's a lot of data that is not going to be migrated into the cloud, and hopefully we find tools that allow us to still access that pretty seamlessly from cloud computing environments, but they're not all in place right now. So there's lots of data that's not searchable, that's hard to find. Some of it's not planned to be. A lot of these legacy data sets are not planned to be transitioned into cloud optimized formats. So there's a lot of work still left to do. So yeah, I'd say absolutely a lot of this infrastructure is not in place yet to really realize what the cloud can provide.
With the CISL seminars here, you're going to get a lot of questions about the third part of your talk. But let me say thanks for the first two parts. Learned a lot about sea ice melt. My question, though, is can you speak to maybe some of the challenges or barriers that you've run into in transitioning to the cloud, either technological or cultural? Yeah,
so we've learned a lot about what it requires to stand up a cloud computing environment as a researcher, because I had no software development background when I started this, and 2I2C is aiming to provide for the scientific community and researchers and educators. So they really wanted to know where the gaps still are for them. And so the big gaps for them were that they had lots of documentation, but it's not super streamlined. So myself as a non-software developer was still struggling a little bit. And the expectation of how much knowledge I should have was different than it needs to be for the scientific community to use this at large, right? So we need someone who has no software background to be able to create a cloud computing or purchase a cloud computing platform from 2I2C. And that isn't quite where they were yet. And I think they're building up to be that. Most of the platforms that they stood up has someone who is really technologically capable. So we found gaps in the documentation in terms of all of that and what is actually going to be feasible to expect from scientists. On top of that, let's see, for our actual users, like I mentioned, a big problem is that A, not all of our data is in the cloud yet, and B, the access to it is crap. The user agreements that we have are huge roadblocks for people being able to access it. Some of our authentication methods, they literally just got streamlined in Earth Access for NASA last week. And so you weren't able to access many of the data sets very easily until that came out. So access and search is still being built. The development is not quite there yet. So our users are not able to use the cloud to its full benefit yet. One thing we learned that was really cool that isn't a barrier is that we can rapidly bring teams in for events and things like that, and they automatically have their environment. It saves a lot of money already having this platform here. So not only are we bringing people on that we expected to in a few of our training events, but other people within the cryosphere are jumping onto our platform for very little overhead. What else are we learning? Most people expect that cloud computing is the future, that in 5 years they'll be doing most of their compute there. We're finding that it's really useful to have a wide range of expertise in the cloud so that the expert users can provide a lot of, like when people ask questions, we have a big user base to respond to those questions, and a lot of our developers. Trying to think, are there any other like realms of questions that you might have that I haven't covered yet? Trying to think off the top of my head.
Any other online questions?
Yeah, there are a couple. So this one's from Negan. Cloud computing has tremendous potential to democratize science by enabling researchers to run simulations from anywhere in the world. However, an important question, who will fund the computational costs required to make this vision a reality for people around the globe?
Yeah.
Oh, sorry.
Oh, go ahead.
There was a comment as well. For example, you mentioned users will bring AWS credits, so it will not be available for everyone in the world.
So our small instances are available for everyone in the world. The larger instances, we just don't have the funding yet to support that. The idea that we're trying to push with the Cryo Cloud is that this is extremely useful for the community, and that means that NASA and other agencies that are the funding agencies should be providing these platforms as a service to their users. In terms of democratizing for people outside of these scientific institutions, that's a little bit more challenging, but potentially there's clouds that we can build that are meant for users to be able to just access and easily use, especially if NASA builds its own cloud infrastructure, then potentially we can start to do that. But working towards these funding agencies providing cloud computing as a service. Like right now, NASA has a HPC that it provides. It has this weird thing called Adapt that no one uses as well, that it provides for free. So it'll be awesome if NASA can soon provide this as a service.
Okay, one last quick question, and then we'll wrap it up.
I thank you for your presentation. I think you kind of mentioned the point I was mentioning, and that is services like Access or Exceed, but now Access, and maybe even NCAR could like make these cloud services available, and that would be a way of merging cloud services and HPC services and allow that to be more accessible to anyone in the world.
Yeah. And potentially there's ways for, our cloud computing infrastructure, or like our actual cloud, to receive authentication for accessing these things. So it provides it for all of our users rather than each user having a separate authentication. So it's some of the questions that we're thinking about too.
Okay, thanks again, Tasha, and thanks to the audience for the questions, and we'll let you know when we have information about the next CISL seminar.
Cool, thank you.